Welcome back. In this video we're going to take a look at implicit differentiation. With implicit differentiation there's no new rules in terms of like product rule or quotient rule or anything like that, but it's a technique of finding a derivative of things that are not functions. So things like circles and ellipses and hyperbolas and things like that. Lots of examples for you. What you're going to do with implicit differentiation is you're going to take a look at something like this. We're going to have an equation something like this where I can't explicitly define y in terms of x. And so what I'm going to do is I'm going to take the derivative of each piece of it, and anytime I take the derivative of something containing y, I need to multiply by dy dx. And then the second piece of the puzzle is to algebraically solve for dy dx. So like when I take this derivative right here, the derivative of y squared is 2y, and because I took the derivative of y, I multiplied by dy dx. The derivative of 3y is plus 3, and again I took the derivative of y, so times dy dx. And then with the x's, I get minus 8x equals 5. And the 1 drops out. That's a constant. So now what I'm going to do is I'm going to group these guys on the left-hand side because they have dy dx, and I'm going to move this one over there. So on the left-hand side, I factor out the dy dx they have in common. In parentheses, it's going to be 2y plus 3. And that equals 8x plus 5. And then finally, in my last step, I'm going to divide both sides by 2y plus 3, so I get dy dx equals 8x plus 5 over 2y plus 3. All the rules of differentiation still apply, so you still have to use product rule, and you still have to use quotient rule, that kind of stuff. What I'm going to show you in my additional examples is that if you have something that where you have like minus xy, you've got to use product rule. If you have a 2 out front, you got to distribute that. So it does get a little bit more complex, but the technique's still the same. In this one, it's a little bit more complex because of this minus 2xy term. The derivative of 3x squared is going to be 6x. I don't multiply by dy dx because I didn't take the derivative of y. I would pull that minus 2 out front, and then in parentheses you want to take the derivative of x times y. So the derivative of x is just 1 times y. You don't multiply by dy dx because you didn't take the derivative of y. Plus the derivative of y is dy dx times x. And then that's plus 8y times dy dx. And then one of the biggest mistakes I see people make is when they take the derivative of 1, they leave it as 1. It's not 1, it's 0. It's a constant. Now distribute this negative 2, so I get 6x minus 2y minus 2x times dy dx plus 8y times dy dx equals 0. We're going to move this stuff over to the right, factor out the dy dx that these guys have in common. So on the left-hand side, I get dy dx times 8y minus 2x equals 2y minus 6x. And then finally divide by what's in parentheses there, so dy dx equals 2y minus 6x over 8y minus 2x. You might see us, they might factor out a 2 and cancel out, so I might have like a 2 times y minus 3x. And then on the bottom I'd have a 2 times 4y minus x. And then cancel out these 2's. You may see that. Just a little algebraically simplifying. The same rules apply in terms of tangent lines and horizontal tangent lines and vertical tangent lines and stuff like that. So a couple more examples. The first one is I'm going to write just the equation of the line tangent to the graph of this equation right here. So I have to use implicit differentiation to find that slope. I'm going to get a slope that's based upon x and upon y. In this problem, I'm just telling you that I want to know where the tangent line is at x equals 1. So I'm going to plug in x equals 1 into the original equation to find the y values. So I'm going to first of all do that. So it's going to be 2 times 1 plus 3y plus y squared equals 6. I'm going to put it in a format that I can factor, so I bring the 6 over. So I'm going to get y squared plus 3y minus 4 equals 0. And then factor that. And when I factor it, I get y plus 4 times y minus 1 equals 0. And then finally, to finish it off, y equals negative 4, y equals positive 1. So the points, there's two different tangent lines when x equals 1, at 1, negative 4, and then at 1, 1. And I'm going to have two separate equations based upon those points, because remember, the derivative is going to be based upon both the x value and the y value. So then to find the slope of the tangent line, I've got to take the derivative of this statement, which is going to be 4x plus 3 times, now take the derivative of x times y, which is exactly the same as the previous screen. So it's going to be y plus x times dy dx because of product rule, and then plus 2y times dy dx equals 0. Algebraically, let's simplify it down. So 4x plus 3y plus 3x times dy dx plus 2y times dy dx equals 0. And then factor out the dy dx. So dy dx, move some things around, equals negative 4x minus 3y over 3x plus 2y. And that's my derivative. And so then if I were to plug in this first point, if I were to plug in this point right here, when x equals 1 and y equals negative 4, then I'm going to get a slope of, for this one, I'm going to get a slope of negative 4, and then it's going to be plus 12 over 3, and then that's going to be minus 8. So if I work that out, I get what? 5 over negative 5, so negative 1. Excuse me, I'm lying to you there. Let's go negative, negative, that's an 8 on top, and it's 5 on the bottom. So then the equation of the line that goes through the point 1, negative 4 is y plus 4 equals negative 8/5 times x minus 1. Do the same thing with the 1, 1. So when I do the 1, 1, the slope is going to be negative 7 over 5. And so it's y minus 1 equals negative 7 over 5 times x minus 1. And then finally, in our last one, my last example, we're going to find the first and second derivative of this equation. The first derivative is just like we've been working on, the implicit differentiation. Just go ahead and do the derivative, multiply by dy dx. So it's going to be 2y times dy dx minus dy dx equals 2. So when I solve it for dy dx, I get 2 divided by 2y minus 1. Now for the second derivative, it's a little bit more complex. Second derivative, first of all, I have this reciprocal function because of this 2 constant on the top. So when I do this, I'm going to use the reciprocal rule, and then I take that derivative of 2y in the denominator. I've got to multiply by dy dx again, which then I'm going to have to end up putting in the first derivative and simplifying it. So the second derivative of this is going to be negative 2, because of reciprocal rule, times the derivative of the denominator, which is 2 times dy dx over the denominator squared. And that's the second derivative. Now I've got to simplify it by putting in dy dx. I put the first derivative in right here. So I'm going to get negative 4 times 2 over 2y minus 1 over 2y minus 1 squared. And when I simplify that, it ends up being negative 8 over 2y minus 1 quantity cubed. That second derivative can get a little bit tricky. It can be algebraically a little bit challenging to simplify it. So we'll clarify this in class best we possibly can. Get your head in the implicit differentiation. Good luck. See you soon.